The world around us is just built from shapes. Some are simple, some seem incredibly complex. But what if I told you there's a hidden order to it all? A simple, elegant logic that governs every single one of them. Well, today, let's uncover the secret language of polygons. We see polygons everywhere, right? Take this gazebo. It's an octagon, which just means it has 8 sides and 8 angles. Pretty straightforward. Or think about an amusement park ride. Its entire structure is a polygon, one that's been perfectly engineered for thrill. Even something as beautiful as a perfectly cut diamond is really just a collection of precise polygonal faces. I mean, these shapes are absolutely everywhere, and they all share a secret. So, that's the big question, isn't it? With all these different shapes, with all their different sides and corners, is there some kind of hidden order to their angles? The answer is a definite yes. And the key to it all is surprisingly simple. It turns out, to crack the code of any polygon, no matter how many sides it has, we only need to start with the simplest one of all, the triangle. The triangle is our blueprint. And the tool we're going to use to crack this code is called a diagonal. Now, all a diagonal is a line that connects 2 corners, or vertices, that aren't right next to each other. This one little line, it's the key to everything. All right, let's try it out. We'll start with a basic 4-sided shape, a quadrilateral. Now, if we just pick one corner and draw the only diagonal we can, boom. Just like that, we've split it into 2 triangles. So a quadrilateral, it turns out, is really just 2 triangles in disguise. And this isn't just some party trick for 4-sided shapes. No way. Let's move up to a pentagon, 5 sides. If we start from a single corner, we can draw diagonals that split it into exactly 3 triangles. See? This pattern is the secret key we've been looking for. Okay, so now that we can see the triangles hidden inside every polygon, let's do a little inside job. Let's figure out the rule that governs all of a polygon's interior angles. Okay, let's just lay out the data. A shape with 4 sides gives us 2 triangles. A shape with 5 sides gives us 3 triangles. And a shape with 6 sides, yep, 4 triangles. Are you starting to see the pattern emerge? And there it is. The number of triangles you can make is always the number of sides, we'll call that n, minus 2. It's that simple. This little relationship is the core of this whole idea. And this leads us straight to something called the polygon interior angles theorem. Now, we all know every triangle has 180 degrees, right? So, to find the total degrees inside any polygon, we just take the number of triangles, which we now know is n minus 2, and multiply it by 180. We've just built a formula that works for any polygon out there. Let's put it to the test with that gazebo from the beginning. That's an octagon, so it has 8 sides. We just pop that into our formula. 8 minus 2 times 180. Well, that's 6 times 180, which gives us 1080 degrees. Perfect. All right, so that's the story on the inside. But what about the angles on the outside? This is where things get really interesting, with a surprisingly simple twist. I want you to imagine you're walking along the edge of any polygon. Every time you get to a corner, you have to turn, right? That turn is the exterior angle. Now, if you could somehow just snip off each of those little turning angles and put them all together, something pretty amazing happens. No matter what the shape is, they always form a perfect circle. Yup, a perfect 360 degrees. Every single time. And that gives us our second huge rule, the polygon exterior angles theorem. It literally does not matter if your polygon has 3 sides or 300 sides. The sum of its exterior angles is always, always, always 360 degrees. So here's this really beautiful contrast, right? The sum of the angles on the inside, it's dynamic. It grows bigger every time you add a side. But the sum of the angles on the outside, it's a constant. It's one of those perfect, simple truths, just hiding in plain sight in geometry. So we've got these 2 really powerful rules. Let's bring them back from the world of abstract ideas and see how they actually apply to the world around us. Okay, here's a trampoline. It's shaped like a regular dodecagon. Now, that sounds fancy, but regular just means all its sides and angles are equal, and dodecagon just means it has 12 sides. Let's use what we've learned. Okay, for the interior angles, we do 12 minus 2 times 180, which gives us the total sum. Then we just divide by the 12 angles to find each one, 150 degrees. Now for the exterior angles, it's even easier.
Just 360 divided by 12, which is 30 degrees. And check this out. At any corner, the 150-degree interior angle and the 30-degree exterior angle add up to 180 degrees, a perfect straight line. It all just connects.
And you know, this whole process is why this stuff matters so much. We didn't just get handed a formula to memorize. We looked at the evidence, we spotted a pattern, and we built a universal rule from our own observations. That process, that's called inductive reasoning. For a few minutes there, we were all acting like mathematicians. And that leaves us with one last kind of mind-bending thought. We saw that for a regular polygon, the more sides you add, the bigger each interior angle gets, right? A square has 90-degree angles. Our trampoline had 150-degree angles. They keep getting closer and closer to 180 degrees. So what happens if you just keep adding sides forever? What does a polygon with infinite sides actually look like? Something to think about.